Welcome back to the Jerusalem Science Contest, week 4. This is chapter 4 that we're going to be doing this week, radioactive decay in greater detail. And this begins on page 51. So we start out by reviewing alpha decay, and if we have some radioisotope X, which has an atomic number of Z, an atomic mass of A, it's going to give up an alpha particle. It's going to transmute to another element. This is now going to be Z minus 2, and this will be A minus 4 to make up for the fact that we're emitting a helium nucleus, which is 2, 4. So now our masses and our atomic numbers are going to be in agreement. And we also want to have the charges agree as well. So we can say if this is going to be 2 plus, because it will have lost 2 electrons, and this will have gained 2 electrons over here. For elements like sulfur and oxygen, this would be the normal dication that you would, dianion that you would expect, something like S2 minus or O2 minus. But if this were, for instance, something like sodium or potassium, those things normally would form cations, not anions. Although you can get a stable monoanion, the stable dication probably would not form. You'd probably wind up losing that electron. Anyway, we can actually look at the energetics of the overall process. And well, first let's look at an example of this, an actual example, which is in your book is curium. So curium 96. 246 emits an alpha particle, and it goes to 94, which is plutonium, 242, and plus your alpha particle. I'm not going to write it down again, but that's what you're actually producing there. And so we can actually look at the energy of the overall process by taking the exact atomic mass of curium. I won't write the whole thing down, but we can actually use the masses that are given in the book, 246.0672. And then if we subtract from that, this is in mass units, if we subtract from that the masses of these 2 particles, so that would be 242.0587. Plus, this is still going to be subtracted, 4.0026, and then we multiply that by the conversion factor that will put this into, take this out of mass units and put it into energy units. So we can multiply that by 931.5 million electron volts per mass unit, and that's going to give us 5.475 million electron volts per nucleon for this overall process for one atom actually decaying. So if we wanted to actually look at the individual particles, we can look at their kinetic energies as well. And one of the things that your book does is it uses the idea that we can do this directly because of the fact that we know that in this kind of a process that momentum is going to be conserved. Momentum in these for an elastic collision, this is going to be conserved. So what's going to happen is that and those of you that are familiar with classical physics know that usually when you write out these momentum kinds of equations, usually in your textbook they usually look something like this. So you'll see something written like that to show you that momentum is conserved. And here you're given something that's a little bit more difficult to see that conservation. What they're showing you in equations 4.1 and 4.2, it says case of alpha equals case of t times the quantity capital M divided by capital M plus small m. So if you look at that, you can actually rearrange that equation so that you're expressing everything in terms of k sub t. And I did that, if I can find it, I wrote it out on a small piece of paper. It might make it a little bit easier. If I can find this little sheet that I did, it might make it a little bit easier to see this. See if I can read it, I can read my handwriting. So what we've got basically is I took the equations 4.1 and 4.2 and I rewrote them, I rearranged them so that I'm solving both of them for k sub t. And then because both of them are in the form of k sub t, I set them equal to one another. So that's k sub alpha times m, capital M plus little m, over capital M. And then that's going to be equal to k sub f times capital M, little m, this time over small m. So this is the kinetic energy of the alpha particle. This is the kinetic energy of the fragment, which is the daughter particle. This is the mass of the daughter, the mass of the alpha, and again, so you've got the same thing over here, but now you've got the kinetic energy of the daughter. So what we can do with that is we can divide now both sides of the equation by m plus capital M plus small m, and that's going to reduce this to k sub alpha over m is going to be equal to k sub f over little m. And finally, we can then substitute in here the fact that the kinetic energy is equal to 1/2 mv squared. So this then is going to become 1/2 m squared v sub alpha, this is little m, I'm sorry, I forgot one step here. I want to multiply everything out here. So I really want to express this as k sub alpha times little m equals k sub f times big M. Now I can actually do my substitution, which is 1/2 m. This is going to give me 1/2 m squared v sub alpha squared. So I had 1/2 mv squared times m, which is where I got the mv squared, and that's going to be equal to 1/2 m capital M squared v sub f squared. And we can then multiply everything by 2. So we've got m squared v sub alpha squared equals capital M squared v sub f squared. And taking the square root of both sides of the equation gives us m v alpha is equal to m capital M v sub f. And that does show you this in terms of the classical momentum. So you can see that these things are equal. So it's basically, we can then use these equations as is done on page 53. You can use this, you can solve for k sub alpha by substituting into the original equation 4.1, and you find out the k sub alpha is 5.386 million electron volts. You do the same thing for the daughter, and you find out that that's 0.0890 million electron volts, which is 89,000 electron volts, kilo electron volts. So you've got that for k sub f. And then the total is going to be the sum of k sub alpha plus k sub f. So if we add in 0.089 million electron volts and 5.386 million electron volts, we get 5.475 million electron volts as the total energy for this system. The difference in energy between the ground and the excited states of plutonium is actually, this is also given here, and we find out that the ground state of plutonium has an energy of 5.343 million electron volts, and the excited state is 5.386 million electron volts. And the difference is small. It's 43,000, 43 kevs, 43,000 electron volts. So ultimately, at the bottom of page 53, what your book does then is show you the decay diagram But there's one interesting feature about this decay diagram, which is in the past, the arrows have always gone right down to the line, and here they don't actually touch the line, which is a little strange, because that would imply that there's a little bit of missing energy. And the author does make the point that there's some uncertainty in calculating the energies, but then he doesn't really clarify whether this is actually due to uncertainty. I don't think it is. I think there is actual some energy discrepancy. Perhaps that energy is heat. I don't really know. There's no indication why these things don't actually touch the line. But what he's showing you are the fact that you've got two different decays here. You've got one decay going from curium 245 down to this excited state of plutonium, and then that emits this 44.5 kilovolt electron, kilovolt X-ray rather, and that takes you down to the ground state of plutonium 242. So, but again, there are those, you know, the fact is that when you actually look at this, the way he's drawing it is something like this, where the arrow here doesn't quite touch the line, and the arrow here doesn't quite touch the line either. But if you sum these things up, this is what we had already calculated, the E total value. That was 5.475 million electron volts right here. Okay, so you know, you can look at this and get some idea. That's how we would actually make a decay diagram for that type of process. There's another example given on page 54. It says show that mass and energy are collectively conserved in alpha decay, and basically what they're doing there is just adding up all of the what we did before, the units, and converting this into the overall. You have 246.067218 units, and that's equal to the 242 plus the 4.04 plus what we've done is taken the energy, that 5.386 million electron volts plus the 0.089 million electron volts, and converted those back into mass units using the inverse relationship, that is having one unit on top and the 931.5 million electron volt unit on the bottom of this. And that gave us 246.067218 units. And it goes, the book also makes the point that this only works if you're looking at the maximum energy alpha particle. If you use the other alpha particle, the 5.343 MeV alpha, which is the weaker alpha particle that might be emitted in this process, then you'd actually have to go back and, so you've got both of these alpha particles, you'd have to go back and then add in the mass equivalent to the X-ray that was actually emitted. So in this process, surprisingly, what happens if you actually look at this process, and we look at N to Z ratios, we find out that when curium goes to plutonium, the N to Z ratio actually increases rather than decreasing. So it started out, the curium started out at 1.56, and when it went to plutonium, it went to 1.57. And you know that we'd actually like to get the N to Z ratio down a little bit. So the only way we can actually do that is by interspersing these alpha decays, since the alpha decay is actually increasing the N to Z ratio. We can intersperse these things, or after we've gone through a number of these things, and then the N to Z ratio gets too high, we can lower it by having a series of beta decays, because the beta decay will actually lower the ratio. So that's also, you can see that on page 54. So that actually is a good segue into beta decay, which is the next thing that we're going to talk about. And beta decay, you'll remember that when that occurs, and there are fundamentally three kinds of beta decays. One of them really isn't a beta per se, it's a positron, but the results or at least the process is similar, has some similarity in all three types, or the end result, I should say, has some similarity, but the processes are actually quite a bit different. So the first thing that you need to know is that in terms of beta decay, there are some fundamental principles or laws that are actually going to determine whether beta decay is going to occur or not, or things that are going to have to be, that will always be true during the process of beta decay. So one of them is that, and this goes back to something that I think I said in the first, probably the first chapter of the book, where the author originally showed the process of beta decay, and he shows it again here for carbon-14. And he says that carbon-14 undergoes beta decay, and it decays to nitrogen-14. And then the beta particle, which is -1, 0, is produced. So all the charges add up very nicely. But I had indicated to you back then that there was something that was missing, and I said eventually the author would get around to correcting it, and he does in this chapter. There's another particle that's produced. Essentially has very, very low mass, so we don't, much smaller than the electron. The electron is already 0, so this is also really 0. And in terms of, it's not changing the atomic number at all, but it's necessary to have this particle in there anyway, because without it, we violate one of the laws, which is the law of conservation. Well, there's a couple things here. First of all, there's a law of conservation of particles. So when a new particle is formed, we have one thing here, something here, a new particle. We say that every time a particle is formed, there has to be an antiparticle. So this is the particle, the electron, and this is an anti-electron neutrino. So this is the antiparticle that goes with the electron. It is produced with the electron. The other thing is the law of conservation of angular momentum. Particles, all the particles, the individual particles, protons, neutrons, electrons, etc. These things have, if we look at, when we're talking about angular momentum, we're really, in a more simple way here, we're referring to what we call spin. And the spin quantum number is going to be 1/2 for all of those particles. So this is going to have a spin quantum number of 1/2, and this is 1/2. And carbon being since all of the protons and the neutrons are paired here, there are 3 pairs. There are 3 pairs of protons and 4 pairs of neutrons. This has a net spin of 0. This one here, nitrogen, has 2 particles that are not paired. One here, one unpaired proton and 1 unpaired neutron, and so each of those has a spin of 1/2. So that has a spin of that's not, should have been an arrow, not a plus sign. This then has an overall spin of 1, and it turns out that you have to conserve the spins as well. The angular momentum has to be conserved. You can go from 0 to some whole number, but you can't go from 0 to a fractional number. You can't go from 0 to 1.5. You can go from 0 to 2, for instance, 0 to 2. That's okay. So if you added all these up, you'd have 2. That would be what we call an allowed process. But going from 0 to 1.5 is not allowed. It's a spin forbidden process. So that's something else that we have to look at. And then, of course, energy also must be conserved. So this is typical of beta decay. And you'll recall also that if we have positron emission, that's going to, in that case, we're going to be producing a positron. Then we won't be producing the antiparticle associated with the positron is the neutrino, not the antineutrino. So, all right. So those are the processes. On page 55, there's also a figure 4.3 down at the bottom of the page, which shows you you can calculate for any of these things, or you can experimentally determine what the maximum energy of emission would be for any of these particles. What I didn't mention before when I was talking about alpha decay is that alpha decay is a quantized type of decay. In other words, the alpha particles only have very, very specific energies. But with these electrons, because you have these in the case of beta decay, because the nucleus could be at any particles in the nucleus could have any particular, could have a whole continuum of energies. You'll get actually a kind of continuous decay. So we don't see the sharp type of thing that we would expect for alpha decay. We don't see we wouldn't see something that would look like, you know, a single energy, but we would have a range of energies. And we'd expect to see something that looked like that. There'd be some kind of a range, and the maximum energy would probably be the calculated maximum energy. We would find that here, and then there'd be some deviation from that. In fact, what we actually see when we do that is we never get the Emax, and we really get something that looks sort of like that. And we'll find out that the actual Emax, the one that we actually observed, not what we've actually calculated, is only about 0.3 of the calculated Emax. So this is where, and we get a much wider range than we would have observed as well for beta decay. And again, that's because of the fact that, you know, there are a lot of different energies associated with that. We never really get up to Emax. Okay, so let's see. So you know, again, if we wanted to write this in the general form of the equation, what we would do is, you know, using the same notation that we did before, we would write for beta decay, starting out with X, and then Z and A, and we've given up beta, so now we're going to be Z plus 1, and A remains the same. We go to Y, and we produce a beta particle, an electron. This is -1 and 0, and so we still get the same total here. We'd actually find, you can even do this also for a free neutron. Neutrons inside the nucleus never undergo this kind of decay. Well, they probably do, but it's the half-life of a neutron that's actually bound in the nucleus is going to be very, very long. It's probably going to be on the order of maybe 10 to the 10th years or something like that. Not true for a free neutron. A free neutron actually has a half-life on the order of about 10 minutes. So neutrons, if they're actually emitted and they haven't struck something, some of these neutrons are actually going to undergo decay if they haven't been absorbed by something. So that will absorb and form a proton. And in order to do that, you have to give up, again, this, and you're also going to form that anti-neutrino. And you could show the same thing for the proton going to the neutron. You could show, which is actually the inverse of this, you could have the proton going to a neutron. And then we have a positron, and this was actually the anti-neutrino here, and here you're getting the neutrino. So that's for both of those processes. And the book gives you again an example on the bottom of page 56. It's showing you scandium decays with the emission of 2 beta particles. And it's just asking you or showing you how to construct the decay diagram. Remember that in beta decay, we're always going to go from here, we're going to go this way, So there are two beta particles. There are two different beta particles. One goes here, one goes there. Then one can decay. One decays from here to here by emission of a gamma. So this is gamma emission right here, and this is we call this beta 1, and this one would be beta 2, or you can designate it however you want. But one of them gives you one of them, the scandium decays to a radioisotope of what is that, thallium, and that's 47, thallium 47, and that's a meta state, an excited state, and then that decays to the ground state of thallium 47. So you can see that on page 57 of your text. Now, it's also possible to get multiple gamma emissions. You can get more than one gamma emission, and that's illustrated on page 58. So you have another example here where and all these gamma emissions are following beta decay. So the beta decay doesn't necessarily always go to the ground state. It could go to an excited state. And when that happens, then you frequently get a gamma emission. But in this particular case, what happens is we have potassium 43 up here. Pardon my handwriting, which is atrocious. Let's try that again. 43K. And that's going to decay to, it's going to give off a 0.83 meg beta particle. So it's decaying to an excited state of calcium 43. Now this is a little unusual because it goes to here. This is calcium 43. Should write it like this. So you've got a metastate of calcium 43, and that gives off a gamma that's going to take this. This is a 617.5 keV gamma, which is actually 0.1675 MeV gamma. So it decays down a bit, but it's still not at the ground state. It then emits a second gamma. So we have gamma 1 and gamma 2 here. Emits a second gamma gamma ray, and that's a 0.3728 MeV gamma, and then you get down to calcium 43. Okay, which apparently is in the ground state now. So you actually have two gammas emitted. There probably is a reason why this transition from here to here is not allowed, and it probably has to do with something that we'll talk about a little bit later, which is parity. It probably violates parity to go from here to here. So we'll see that maybe a little bit later on. So you actually have to do this in two steps.